Good morning. I'll continue the discussion on gas turbine cycle analysis. Contents of the lecture are regenerative cycle, reheat cycle. I'll derive the expression for specific work output and efficiency. I'll initiate the discussions with heat exchange cycle, that is a regenerative cycles. In most cases, the turbine exhaust temperature is higher than the outlet temperature from the compressor. Thus, the exhaust heat can be utilized by providing a heat exchanger that reduces the heat input in the combustion chamber. Hence, the saving of energy increases the efficiency of the regenerative cycles, keeping the specific output unchanged. A regenerative cycles, these operating principles will be illustrated in the next page. A simple gas turbine cycle with a heat exchanger has been illustrated in figure 4. It constitutes of a compressor, turbine, and a generator as before. The turbine is connected to the compressor, so turbine output utilized in running the compressor at the same time in running the generator to produce electricity. However, here a heat exchanger is provided between the compressor and the turbine. Thus, air initially is being compressed and then passing through the heat exchanger. Then the combustions occur in the combustion chamber and then pushed to the turbine. It is being expanded, and then the exhaust is passing through the heat exchanger. That there is an exchange of heat of the exhaust gases to the air following the combustion chamber. Thus, 1, 2, 3, 4, 1. As before, the 3S diagram of a simple gas turbine cycle. Here, the part of the heat load is accomplished in the heat exchanger, that is, the process 2-5 occur because of exchange of heat in the heat exchanger. So now the heating occur in the process 5-3 in the combustion chamber. Therefore, heat added to the cycle has decreased, increasing its efficiency. However, the specific work output remains unchanged. Here, we have considered the heat exchanger as perfect. That means I am considering T5 is equal to T4 and T2 temperature at the point 2, state point 2 is equal to T6. The efficiency of a regenerative cycle can now be expressed as eta is equal to turbine work minus compressor work divided by heat added to the cycle. Thus, eta equal to Cp minus T3 minus T4, that is turbine work, minus Cp into T2 minus T work, that is work required by the compressor, divided by heat added to the cycle would be now equal to T3 minus T5. Now the part T5 to T2 would be taken care by the heat exchanger. Now for ideal heat exchanger, we have assumed T5 would be equal to T4. Thus, in the expression of heat added, T5 would be replaced by T4. Hence, the efficiency of the cycle can be expressed as eta is equal to Cp into T3 minus T4 minus Cp into T2 by T1. Numerator remains same. However, denominator would be Cp into T3 minus T4. Thus, considering Cp is constant, so eta is expressed as 1 minus T2 by T1 divided by T3 minus T4. Now take T2 common from numerator and from denominator take T3 is common, so if it can be expressed as 1 minus T2 by T3 within the bracket 1 minus T1 by T2 divided by 1 minus T4 by T3. Now, considering the isentropic relations between P1 and P2, I can express as T2 by T1 is equal to P2 by P1 to the power gamma minus 1 by gamma is equal to T3 by T4. P2 by P1 is considered as the pressure ratio of the cycle and expressed as R. Thus, T2 by T1 is equal to T3 by T4. Considering this, the expression of eta would be this within the bracket would cancel, so it would be equal to eta is equal to 1 minus T2 by T3. That can be written as 1 minus T2 by T1 into T1 by T3. Now we know T3 by T1 I have denoted as small t, where T3 being maximum cycle temperature and T1 is the atmospheric temperature. So thus eta is expressed here as 1 minus C by T. Please note that eta here is dependent on the maximum cycle temperature. If you remember the expression of eta for a simple gas turbine cycle, eta was independent of maximum temperature of the cycle, but here, apart from pressure ratio, it is dependent to the small t, that is temperature ratio T3 by T1. So not here eta, again I'm repeating, not here, eta is equal to 1 minus C by T. Thus cycle efficiency will decrease with respect to pressure ratio, increase of pressure ratio, and it will increase with respect to increase of temperature ratio. Figure 5 illustrates the efficiency of a simple gas turbine cycle with heat exchanger. Look, efficiency is a function of both temperature ratio, small t, and pressure ratio. Now, as temperature ratio increases, the efficiency increases. Similarly, for a certain temperature ratio, say small t is equal to 3, as pressure ratio increases, the efficiency decreases, and it will terminate at a point where the efficiency becomes equal to that of a simple gas turbine cycle for optimum power output. As I have stated earlier, figure 5, which is presented here, represents the characteristics of a simple gas turbine cycle with heat exchanger. Here, efficiency is not independent of maximum temperature of the cycle. Rather, the efficiency of a regenerative cycle depends on both temperature ratio and the pressure ratio. Furthermore, the efficiency increases with T, but it decreases with increase of R. Now look, for each constant T curve, it starts at R is equal to 1, having a value of efficiency is equal to 1 minus 1 by T, that is the efficiency of a Carnot cycle. That means each constant T curve starts at R is equal to 1, having a value of efficiency of the Carnot cycle. Furthermore, the curve for each T falls with increasing R until a value corresponding to R to the power gamma minus 1 by gamma is equal to root over T is reached, where efficiency reduces to that of a simple gas turbine cycle for maximum work output. That means, what I like to say, at the point of interaction here, which have been expressed by the dotted line, locus of all points of interactions, the dotted line represents the efficiency of a simple gas turbine cycle. With respect to figure 5, further, at the point of interaction, I have indicated that efficiency of the regenerative cycle would be equal to efficiency of a simple gas turbine cycle. Thus, I can write eta is equal to 1 minus C by T is equal to 1 minus 1 by C. So 1 minus 1 by C, that denotes the efficiency of a simple gas turbine cycle, and 1 minus C by T denotes the efficiency of a regenerative cycles. This equation leads to T is equal to T square. That means T2 is equal to T4. Hence, the curves for each T falls up to the pressure ratio for which the specific output becomes maximum, that is T2 is equal to T4. Furthermore, I like to state that I have assumed the heat exchanger is perfect. That means for an ideal heat exchange process, I can say T4 is equal to T5 and T6 is equal to T2. However, in reality, the heat exchange takes place when T4 would be greater than T5. I now illustrate gas turbine cycle with reheat. Reheat is done to enhance the specific power output. Look here, the expansion process has been divided into two turbines. One is referred as high pressure turbine HPT, followed by a low pressure turbine LPT. Thus, air is compressed in the compressor, then heat added in the combustor. After that, high pressurized and temperature gas is expanded in high pressure turbine. Then exhaust from HPT is reheated in the reheat combustor, and then again it's expanded through LPT turbine. The turbine work is used to run the compressor and to run the generator to develop the electricity. So look, figure 6 illustrates a reheat cycle. So 1, 2 is the compression process, and then 2, 3 is the heat addition in the combustion chamber. 3, 4 is the expansion in HPT, high pressure turbine. 4, 5 again is the adding of heat in reheat combustor. And then 5, 6 expansion in low pressure turbine. And the 6, 1 completes the cycle. So 1, 2, 3, 4, 5, 6, 1 is the reheat cycle here, where both compression and expansion processes are considered isentropic. Look here, after heating, the temperature of the cycle, T5, is considered here equal to T3, maximum temperature of the cycle. So generally, it's heated like that, T5 is equal to T3. Please note that a substantial increase in specific work output can be obtained by splitting the expansion and reheating the gas between the high pressure turbine and low pressure turbine. Furthermore, reheat increases the mean temperature of heat addition, and also the mean temperature of heat rejection is increased by reheating, resulting in a decrease in thermal efficiency of the plant. Thus, the specific output is increased while the efficiency decreases because of reheating. Furthermore, I can say the reheat cycle, which is 1, 2, 3, 4, 5, 6, 1, that's the reheat cycle, is the combination of two simple gas turbine cycles, 1, 2, 3, and 4 dash, and 4 dash, 4, 5, 6. So, reheat cycle is the combination of the two cycles stated as 1, 2, 3, 4 dash, and 4 dash, 4, 5, 6. Now the cycle 4 dash, 4, 5, 6 has a lower pressure ratio, and thus the lower efficiency. Hence we can say the combination of the two, which is the reheat cycle 1, 2, 3, 4, 5, 6, has an efficiency which is lower than that of the simple gas turbine cycle having a pressure ratio P2 by P1. Let us carry out now the performance analysis of a reheat cycle. Thus, the specific work output can be given by W equal to the work done by the two turbines minus compressor work. So it would be Cp into T3 minus T4 plus Cp into T5 minus T6. This one represents the work done by HPT, and this one is work done by LPT. Minus compressor work is equal to Cp into T2 minus T1. Now look here, the total work that Cp into T3 minus T4 plus Cp into T5 minus Tc. The summation must be greater than Cp into T3 minus T4 dash. Thus, because of reheating, the work output has increased. Furthermore, the efficiency of the reheat cycle can be expressed as work output divided by heat added. So that work output is equal to W, that is Cp to T3 minus T4 plus Cp into T5 minus T6 minus Cp into T2 minus T1. Now heat added would be equal to now in the combustion chamber plus reheat combustor. Now that must be equal to Cp into T3 minus T2 plus Cp into T5 minus T4. That Cp into T5 minus T4 is the heat added during reheating. So this is the expression for efficiency of a reheat cycle. Now assuming the gas would be reheated to the same temperature T3, the specific output would be optimum when the pressure ratio, that is the temperature and work transfer for the HP and LP turbines are equal. So what I like to state that specific output of the cycle, reheat cycle, would be optimum when the pressure ratio of each turbines would be equal. With this optimum division, it is then possible to derive the expression for the specific work output and efficiency in terms of C and T, where C is equal to R to the power gamma minus 1 by gamma and T being T3 by T1. Thus, when the pressure ratio for both high pressure turbine and low pressure turbines are equal, then specific work output and efficiency can be expressed as W divided by Cp into T1 equal to 2T minus C plus 1 minus 2T by root over C, or eta equal to 2T minus C plus 1 minus 2T by root over C divided by 2T minus C minus T by root over C. Thus, specific work output and efficiency are expressed in terms of T and C. Well, in conclusion, I can say that the specific work output is remarkably increased because of reheat, and this is achieved at the expense of efficiency. Thus, the efficiency of the reheat cycle will decrease or will be less than the simple gas turbine cycle. Characteristics of the reheat cycle is expressed in figure 7. Here, efficiency is expressed in terms of pressure ratio, this figure. Here you will find that efficiency for the reheat cycle lies below the efficiency of the simple gas turbine cycle, illustrating that reheating decreases the efficiency, while the specific work output is presented with respect to the pressure ratio. And from this figure it has been realized that reheat cycle's specific work output is more than the simple gas turbine cycle. Hence, I have concluded that the regenerative cycle is used to enhance the plant efficiency, while the reheat cycle is used to increase the specific work output. Thank you for listening.